I'm speaking about the computational tractability of a geographic clustering problem arising in redistricting. So what is redistricting? Redistricting involves dividing a geographic region, such as a state, into subregions called districts, each of which will select a representative. And the district should be population balanced. So in the US, every 10 years, a census is taken, and the populations are used to design new district plans. Now, in the US, the Constitution assigns to the legislature of each state the job of redistricting. And because each district's proportion of voters in different parties influences the outcome of the election, this gives the legislators an opportunity to influence the election results. Gerrymandering is engineering a district plan to achieve some unsavory political goal. Now, even if you agree with a particular political goal, there is a moral case against gerrymandering because the government should really not be in the business of treating voters as a means to an end. And the government should also not seek to give more political power to some people than others based, for example, on their political preferences. The primary goal of our research is to put sophisticated computational tools in the hands of those who seek to redistrict without gerrymandering, who seek to do nonpartisan redistricting. Now, a secondary goal of the research is to provide provably correct algorithms for uniform random sampling of district plans. And this is something that has been used in court cases to challenge existing district plans. Now, in France, there's a plan to change the size of the legislature, which will require redistricting. And a research team, including one of my co-authors, sought to enumerate for every department, it's analogous to a state in France, for every department, enumerate all the legal district plans for that department. And they mostly succeeded, but there were several departments where there were just too many. They couldn't enumerate them all. And that's what prompted this research project. We wondered, can we address this problem algorithmically? Can we come up with an algorithm that for every department in France can find an optimal district plan? Now, when you ask for an optimal district plan, you better know what constraints there are and what's the objective. So I want to go over some principles of redistricting before we get into the technical side. What principles should govern the design of a district plan? Now, at a very broad level, I want to say that a district plan should treat people equally to the extent permitted by law, and the process should be fair. We're not making any guarantees as to the outcome being fair. And finally, the process should be transparent. To my way of thinking, the answer is to set up an optimization problem, finding the best district plan, and to decide on the best district according to those criteria. And now, here are the broadly accepted legal redistricting criteria, at least in the US. The district should achieve population balance. That is, two districts in the same state shouldn't differ in their population, or shouldn't differ by much. The district should be contiguous, which to those of us in graph theory means connected. And finally, the districts should be compact regions. What that means is subject to a lot of debate. We'll give one criterion later. Today, we're focusing on a specific kind of redistricting problem, which I call a discrete coarse redistricting problem. Here, the state to be redistricted is made up of atomic regions, and a district plan is a partition of these atoms. So, for example, Kentucky requires that districts mostly preserve whole counties. So if we require that they all completely preserve whole counties, then the counties would be the atoms. France requires that each department's districts preserve cantons. So in this case, the cantons are the atoms. So in this discrete redistricting problem, the goal is to find a partition of the atoms. Let K be the target number of parts, that is the desired number of districts. Then we're trying to find a K partition of the atoms, a K partition that balances population to within a given tolerance. So that satisfies the population balance criterion. We want each part to be connected. So that satisfies the contiguity criterion. And finally, we want the entire partition to minimize the total cost of cut edges, and that will be our measure of compactness. So what are cut edges? Well, let's zoom in on the map of Kentucky showing the atoms. And suppose this red outline is one district. Then the corresponding cut edges are pairs, are edges that connect adjacent atoms that are in different districts. So these are the cut edges corresponding to this one district. Now, one criterion for compactness that's been proposed by the metric geometry and gerrymandering group led by Munduchin is to minimize the number of cut edges overall produced by the district plan. We said that, so that one goal is to find a partition that has these properties, and a related goal is to uniformly sample from feasible partitions, possibly subject to a budget on the number of cut edges. Now, these are NP-hard problems, even for planar graphs, which is the graphs that we're looking at here. Can we further restrict the input to make the problem easier? Here's how we're going to do that. We're going to look at graphs of bounded branch width or tree width. Branch width and tree width are measures of the complexity of a graph. Loosely speaking, they're a measure of how many edges must be removed to break up a graph. Branch width and tree width are closely related. They're within a constant factor of each other. Now, in planar graphs in particular, if the diameter of the graph of atoms is, say, d, then the branch width is at most d. So here we see that the Kentucky graph of atoms has branch width at most around 7, and the French department, Sarth, has width around 5. Now, in previous work, some members of the metric geometry group, motivated by redistricting, considered the problem of randomly sampling K-way connected partitions of graphs of bounded branch width or tree width. They showed that this is possible theoretically in order n log n time. Now here they're ignoring population balance. Now the big O constant here hides a dependence on the parameters K, the number of districts, and W, the width of the input graph. And in fact, in their result, the big O is quite big indeed. The constant is a tower of exponentials in K and W. But theoretically, we would say a result of this kind shows that the problem is fixed parameter tractable in the parameters K and W. And the authors question whether this can be extended to require population balance. And we show that the answer is no. So as we said, for fixed K and W, there are n log n time algorithms for partitioning a width W graph into K connected parts and for generating such partitions uniformly at random. So far, we're not considering population balance. We say that these problems are fixed parameter tractable with respect to W and K because the runtime is polynomial and the degree of the polynomial is independent of W and K. Basically, the big O constant hides the dependence on W and K. And in our first result, we show that the corresponding problems in which population balance is required are not fixed parameter tractable with respect to W and K. That is, there's no constant degree C such that there's a polynomial time running time where the degree of the polynomial is C, independent of W and K. Now, this is under a standard complexity theoretic assumption. We'll talk about that in a moment. A stronger version of this theorem, based on the same reduction, shows the following, that for any k sufficiently large, there exists a width W such that for any epsilon greater than 0, there is not an algorithm that runs in this running time. So this seems to suggest that the running time of an algorithm would have to be of the form n to the W plus k. Now, this is, again, under a standard complexity theoretic assumption, this time the exponential time hypothesis. We have a complementary theorem giving an upper bound that, in fact, these problems are fixed parameter tractable with respect to each of those two parameters separately. So the problems are fixed parameter tractable with respect to W and fixed parameter tractable with respect to K. In particular, you can get an algorithm with a polynomial running time where the degree of the polynomial depends just on K, not on W, or just on W and not on K. We also have empirical results that indicate that this algorithm is not purely theoretical, that there is a practical implementation of this algorithm. First, I'll go over Theorem 1. The analog of NP hardness is called W1 hardness. That's the analog for showing that a problem is not fixed parameter tractable with respect to a given parameter. So Theorem 1 really states that the problem of K partitioning of a width W planar graph into connected parts of the same weight is a W1 hard problem. And just as with NP hardness, the way to show a problem is W1 hard is to reduce a problem that's already known to be W1 hard to your new problem. We'll do that using a reduction from a problem called K-bin packing. The input to K-bin packing is a target integer B and n integers V1 through Vn. The output must be a K partition of V1 through Vn such that each part sums to B if such a partition exists. And determining whether such a partition exists is W1 hard. That's been shown in the past. So what we're going to do is briefly summarize the reduction we use from K-bin packing to this problem of partitioning a planar graph into connected regions of the same weight. So given an instance of K-bin packing, the reduction constructs this grid-like graph. Now, the grid-like graph consists of K columns, and as a consequence, the tree width and the branch width are order K. And the vertices of the graph have weights as given here, and the target weight is as given here. It's easy to see that any region of weight at least this quantity, kb squared plus kb to the fourth, must contain a vertex from the top, one of these green square vertices, and a vertex from the bottom, one of the pink hollow circular vertices. Now remember, the target weight is more than that. We can use this to show that any feasible solution to this partitioning problem consists of K regions, each having one of those green square regions, green square vertices, one of the pink circular vertices, and n blue vertices, one for each of the rows of this grid. Now, if you take just all the vertices in a single column, let's say the leftmost column, it'll total to this quantity, which is not quite the target quantity. It's short by b from the target quantity. As a consequence, in order to get a region that has the correct weight, it's not enough to take just a column. The column must also borrow some of the red vertices from the adjacent column, the column to its right, just like this. So to create a bin, you add the red vertices from the column to the right, corresponding to the values vi that form the part whose total weight is b. So as a consequence, there's a solution to the bin packing problem if and only if there's a way to partition this graph into connected regions of the desired weight. Now I'll say a few words about the upper bound. So here I've given the runtimes that are achievable for unit weights using big O in the exponent. Now, there is previous work that shows that the partitioning problem is fixed parameter tractable with respect to k. And here's the running time that they achieved, even for general graphs. So here are a few remarks. One, those constant factors in the exponent really matter. For example, that term n to the 2w plus 3 is pretty tough. Fortunately, the constants can be reduced for planar graphs. So we can get bounds. We can show that these problems are FPT, fixed parameter tractable with respect to k and with respect to w. The more important result for our application is where k is small, where k shows up in the exponent of n, because k tends to be smaller than w. So the best bound that we can show in that regime looks like this for unit weights. More generally, if the part weight is less than or equal to u and the solution cost is less than or equal to s, then this is the running time looks something like this. And the method is a fairly straightforward dynamic program, plus the use of the fast Fourier transform. So the dynamic program uses the recursive decomposition into clusters that's implied by the branch width being bounded by w. So branch width being bounded by w means that there's this recursive decomposition into clusters where each cluster has a vertex boundary of size at most w. The dynamic program consists in building a cost table T for each cluster in this recursive decomposition. The cost table is indexed by configurations. So a configuration specifies first the internal connectivity partition that's supposed to be established by using edges inside the cluster. And in planar graphs, the number of such things is c to the w for a constant c. It also specifies the external connectivity partition, which is what connectivity is going to be established by adding edges in as we go up to ancestor clusters. And similarly, the number of such external connectivity partitions is at most c to the w. This is using planarity and the fact that these connectivity partitions are non-crossing. And finally, we need to specify a vector, a k vector of the populations of the parts. So it looks like that. And the number of such k vectors is bounded by u to the k. The number of configurations overall is the product of those three quantities. And computing the table for the parent from the tables for the children clusters is done efficiently using the FFT. Finally, I'll say a few words about the dynamic programming algorithm in practice. We implemented the algorithm, a simplified version that doesn't use the FFT, and we were able to use it to find optimal district plans for all the departments of France. We didn't attempt Paris, which goes by different rules. Now, the French law requires that the population disparity is at most 20%, but the algorithm actually often finds more balanced district plans. So on the left, we show the optimal district plan for the department Sarthe with the target of 4 districts. That's the correct target. On the right, just for fun, we show the decomposition with 7 districts. In the last few slides, I'll just show the solutions for all the departments in France other than Paris. Note that some departments require only 1 district. So in those cases, the redistricting problem was pretty simple. And that's it for my talk.